Hello, and welcome to Astronomy Daily for Tuesday, the 14th of July, 2026. I'm Anna.
And I'm Avery. Episode 140 of Season 5, and honestly, today's rundown reads like someone dared us to pick the most argument-starting stories we could find.
It really does. Coming up, American regulators have just approved the launch of the first commercial space mirror, a spacecraft designed to beam sunlight down to Earth at night. And astronomers are, let's say, not thrilled.
We've also got a newly revealed minefield of invisible space junk in one of the most valuable orbits around Earth, with an Australian telescope right in the middle of the detective work. Plus, physicists in Manhattan have recreated black hole energy extraction in a lab. The biggest telescope ever built just moved for the very first time. And a new paper explains how the Square Kilometre Array is about to turn cosmic lightning flashes into a map of the invisible universe.
And later, a quick update on Starship Flight 13 and the story of the Harvard astronomer who's just been handed the keys to the White House's new UFO Science Council.
Told you, argument starting. Let's get into it.
Our lead story today. On the 9th of July, the U.S. Federal Communications Commission formally authorized the launch of Arendelle-1, a demonstration satellite from California startup Reflect Orbital. Once in orbit around 600 kilometers up, it will unfurl a thin film reflector 18 meters on a side, that's roughly 60 feet, and use it to bounce sunlight down to specific spots on the ground for several minutes at a time.
So, to be clear for everyone, a giant steerable mirror in space whose entire job is to shine daylight onto the night side of Earth.
That's exactly it. The company calls itself the Sunlight Company, and the pitch is sunlight on demand, lighting construction sites so crews can work through the night, illuminating search and rescue operations, and boosting solar farms by extending their generating hours past sunset.
The demonstration satellite weighs about 142 kilograms and is due to launch later this year. And here's the number that makes this a much bigger story than one test satellite. Reflect Orbital has talked about operating 50,000 or more of these mirror craft in low Earth orbit by 2035.
Which is why the astronomy community has reacted the way it has. The FCC application drew nearly 1,900 public comments, the overwhelming majority critical. For comparison, SpaceX's application for up to 1 million orbital data center satellites drew about 1,500. The European Southern Observatory has described plans like these as an existential threat to optical astronomy.
And it's not just professional observatories. The American Astronomical Society raised the prospect of eye damage for amateur astronomers. The company itself has acknowledged there's a risk if someone happened to catch the reflected beam through a telescope with a large enough aperture. Plus, concerns about momentarily dazzling pilots, and about what artificial daylight does to wildlife. Circadian rhythms are not optional extras for most living things.
The FCC's answer to all of that was essentially not our department. The commission said concerns about optical astronomy and the environment fall outside its review, which is limited to radio spectrum. It found the risks with a single satellite unlikely to materialize and said testing novel technology is in the public interest.
Which might be true for one satellite. One mirror, tested carefully with the light contained, switchable, and steered away from observatories. That's a technology demonstration. 50,000 of them is a different planet to live on. And the regulatory gap is the real story here. If the agency licensing these satellites says impacts on the sky aren't their job, then whose job are they?
To be fair to the company, they say they're trying to earn trust. The light is contained within the target spot, it can be switched off at any moment, and they'll avoid sensitive areas like research observatories and protected habitats. Their co-founders said this license is the first step toward rigorously testing both the technology and the safeguards.
And that test data will matter, but I suspect this is one we'll be covering again and again.
The satellite's named Arendelle, by the way. Tolkien fans will recognize the mariner who sails the sky with a shining star on his brow.
At least they've got good taste in names. Whether the night sky agrees is another matter. Okay, from mirrors we can see to junk we can't. A new study led by the University of Warwick has uncovered some of the faintest space debris ever detected in geosynchronous orbit. Fragments down to about 5 centimeters across. That's 2 inches. And here's the kicker. Nearly 80% of the faint objects they found don't appear in any publicly available catalog.
Let's set the scene for anyone new to this. Geosynchronous orbit is that special band about 36,000 kilometers up, where a satellite circles the Earth exactly in step with our planet's rotation, so it hangs over the same spot. It's home to the big, expensive workhorses: communications, broadcasting, weather monitoring. Some of the most valuable real estate in space.
And unlike low Earth orbit, there's no cleanup service. Down low, the wisps of atmosphere gradually drag debris down until it burns up. At GEO altitude, there is essentially nothing. Whatever ends up there, a dead satellite, a fragment from a breakup, stays there, effectively forever.
So how did they find pieces this small at that distance?
Clever image processing rather than new hardware. The team went back to archival survey data from the Isaac Newton telescope in the Canary Islands and applied a technique called blind stacking, layering many images along different possible trajectories so that incredibly faint moving objects rise up out of the noise. That reprocessing revealed 25 debris track lips the original analysis had completely missed. And the brightness flickering of many of these fragments shows they're tumbling as they drift.
And there's a lovely local connection in this one. The follow-up observing campaign extended the survey to Siding Spring Observatory here in Australia, working with the Australian National University plus Japan's Bisei Space Guard Center with JAXA. Genuinely international detective work, which makes sense because the GEO belt is a shared resource.
The study's lead author, Dr. James Blake, pointed out that pieces of junk up there can be moving at kilometers per second relative to each other. So even a 5-centimeter fragment carries enough energy to do serious damage to a very expensive satellite. And his co-author, Dr. Stuart Eaves, had the line of the week. The debris in geosynchronous orbit is a potential minefield, and nobody in their right mind walks into a minefield without a mine detector.
The constructive takeaway being, we now have the detection techniques. Deeper, systematic surveys of the GEO belt need to become routine because there are only so many orbital slots up there, and one bad debris event could poison a chunk of that belt for generations. Now to a story that's been making headlines this week, and it's a proper piece of physics history. Researchers at the Advanced Science Research Center at the City University of New York have recreated in a laboratory the mechanism by which energy can be extracted from a spinning black hole. The paper's in Nature.
Okay, walk me through the black hole part first, because it's one of the great ideas of 20th century physics.
It goes back more than half a century to Sir Roger Penrose. A spinning black hole drags the very fabric of space around with it in a region called the ergosphere. Penrose realized that if a particle ventured in there and split in two, one piece could fall in while the other escaped, carrying more energy than the original particle arrived with, energy stolen from the black hole's rotation. The physicist Yakov Zeldovich then extended the idea to waves. Bounce a wave off a sufficiently fast rotating object, and the wave can come away amplified. That effect is called superradiance.
And the problem for 50-odd years has been the words sufficiently fast. You can't mechanically spin anything quickly enough. There were beautiful experiments with water vortices in 2017 and a rotating acoustic disk in 2020. But physically spinning objects hit a hard ceiling.
Which is where the New York team's trick comes in. They call it synthetic rotation. Instead of spinning anything at all, they built a ring of electronic resonators and rapidly modulated their electrical properties in a timed sequence running around the ring. To an incoming radio wave, the stationary device is indistinguishable from something rotating impossibly fast. The synthetic rotation can even mimic motion faster than light, which no physical object could ever achieve.
And it worked. the waves actually came out stronger.
They did. The team measured genuine amplification, with waves extracting energy from the synthetic rotation exactly as Penrose and Zeldowich predicted. Nothing moves, yet the wave leaves with more energy than it arrived with.
What I love about this one is that it cuts both ways. It's a fundamental physics validation, a 50-year-old prediction about black holes confirmed on a benchtop in Manhattan, but it's also a brand new kind of amplifier, with a team talking about applications in wireless communications, optics, and quantum technologies. Astrophysics as an engineering department.
Black holes inspiring better radios since 1969. Who knew?
Next, to a mountaintop in Chile's Atacama Desert, where the biggest optical telescope humanity has ever attempted just did something for the very first time. It moved.
This is the European Southern Observatory's extremely large telescope, the ELT, under construction on Cerro Armazones. Crews rotated the telescope's entire structure around its vertical axis for the first time. And in the most charming detail of the week, they started by pushing it by hand a few centimeters before completing a full rotation with auxiliary motors. ESO captioned the release, "And yet it moves," which Galileo would surely have appreciated.
Now, let's put numbers on why hand-pushing this thing is remarkable. The structure currently weighs about 3,500 tons. Once the mirrors and instruments go in, it climbs to around 4,600 tons. And the whole assembly floats on a film of oil just 80 microns thin, roughly the width of a human hair. That's how a handful of people can start 10 million pounds of telescope turning.
And this wasn't ceremony. It was a critical engineering test. That rotation is how the ELT will point anywhere in the southern sky. So proving the motion is smooth is a genuine milestone on the road to first light. When it's complete, the ELT's segmented primary mirror will stretch 39 meters across, built from 798 hexagonal segments, working as one. It'll gather more light than any optical telescope in history.
ESO's program manager, Roberto Damai, said it beautifully, that it's a reminder of what can be achieved when people push in the same direction, literally and figuratively.
And for our listeners, remember this giant lives under southern skies. The Magellanic Clouds, the galactic center overhead. The ELT will see the same sky you do from your backyard, just 40 million times better.
Rude, frankly, but we'll allow it.
Sticking with giant instruments and southern skies, a new paper doing the rounds this week lays out how the Square Kilometre Array is going to use one of the most violent phenomena in the cosmos to map things no telescope can see. And the lead author is Dr. Manisha Caleb of the University of Sydney.
Home team, all right. The violent phenomenon in question being fast radio bursts?
Fast radio bursts, flashes of radio energy from other galaxies that last about a millisecond, 100 times quicker than a blink, yet carry enormous energy. And they're useful precisely because of what happens to them on the way here. As a burst crosses billions of light years, the plasma it passes through disperses it, stretching the signal out by frequency, and magnetic fields twist its polarization through an effect called Faraday rotation. Every burst arrives carrying a record of everything it traveled through.
So each one is like a core sample drilled through the universe. The gas between galaxies barely emits any light, and magnetic fields emit none at all. But you can read both from what they've done to the burst along the way.
Exactly. And the paper's argument is about scale. We've caught FRBs by the hundreds so far. The SKA, with SKA low being commissioned right now in Western Australia, alongside the Dish Array in South Africa, is expected to detect them in the thousands upon thousands. At those numbers, the team argues FRBs graduate from curiosities into a genuine cosmological survey tool, tracing where the universe's missing ordinary matter is hiding, mapping cosmic magnetic fields, probing the universe's expansion, even testing fundamental physics, like whether photons have any mass at all.
And the poetry of it is that we still don't fully know what makes a fast radio burst. Magnetars are the leading suspects, but the case isn't closed.
So the SKA gets to work the mystery from both ends, using the bursts as tools while simultaneously figuring out what they are.
A telescope partly in our own backyard using millisecond flashes from across the universe to weigh the invisible. The next few years of this are going to be something special.
Next up, a quick update on Starship Flight 13. We gave you the full preview in yesterday's episode, so just the new developments today. First, the launch date has slipped. SpaceX is now targeting no earlier than Thursday, the 16th of July at 6:45 in the evening U.S. Eastern Time. That's 8:45 Friday morning for those of us on Australia's East Coast.
And second, the good news that came with the slip. SpaceX has completed a full static fire of the Super Heavy booster, lighting all 33 Raptor engines on the pad. That's the final major test before flight.
The mission itself is unchanged from what we covered yesterday. The second flight of the version 3 vehicle carrying the first genuinely functional Starlink V3 satellites rather than mass simulators. If the schedule holds, we'll have the full story in Friday's episode.
Set those alarms, Australia. A Friday breakfast launch is the civilized way to watch Starship fly. Now, in case you missed it over the past couple of weeks, and because it's simply too interesting to leave on the shelf, Harvard astrophysicist Avi Loeb has been appointed to chair a brand new White House UAP Science Advisory Council, a scientific panel tasked with investigating unidentified anomalous phenomena. That's the current official term for what everyone still calls UFOs, covering objects in the air, in space, or even underwater.
And for listeners who know the name, yes, that Avi Loeb, former chair of Harvard's astronomy department, hundreds of papers on black holes and the early universe, and in recent years, the most famous or infamous advocate for taking the possibility of alien technology seriously. He's the one who suggested the interstellar object Oumuamua might have been an artificial light sail back in 2017.
The setup, the council was established under the Trump administration's transparency push on UAP, alongside agencies including the Pentagon's Anomaly Resolution Office, Office of the Director of National Intelligence, and the FBI. Loeb's team reports to a new UAP governance board overseen by the intelligence community. And after its first meeting, the council requested more than 50 videos, images, and documents from the Pentagon tied to known incidents, including the so-called orb sightings reported by military personnel.
Now, the scientific community's reaction has been divided, is the polite word. John Kirkpatrick, who used to run the Pentagon's own UAP investigations, said Loeb is not viewed favorably by much of the scientific community and lacks national security experience. Critics point to his hand-picked council, including not just data scientists and oceanographers, but also figures who've openly claimed the U.S. has recovered non-human craft.
And in fairness, here's the other side of the ledger. Loeb himself says he's starting from the assumption these objects are human-made and treating it as a national security question. He says the government is genuinely baffled by some of what it's seen, and his argument is that the fact these cases are being open to scientists at all suggests officials aren't confident they're conventional. His stated focus is instrumentation, data standards, and rigorous collection. In his words, better data could settle the alien debate once and for all.
And that's the version of this I can genuinely get behind. The worst outcome for a question like this is that it stays in the realm of blurry footage and anecdote forever. If this council produces calibrated instruments and open data, that's a win, regardless of what the answer turns out to be. If it produces headlines instead of data, well, we'll report that too.
His own line on it, keep our eyes on the orbs, not the social media.
On this show, we keep our eyes on both, strictly professionally.
Time for your Skywatch, and tonight is genuinely one to circle. The 14th of July brings a super new moon, which means the darkest skies of the entire month. And for those of us in Australia and New Zealand, that's a standing invitation. The Milky Way's core is riding high through the evening, with Scorpius and Sagittarius nearly overhead. If you've been meaning to get somewhere dark and see our galaxy properly, tonight and the next few nights are the time.
While you're out there, look west after sunset for Venus, absolutely blazing at around magnitude -4 in Leo. You can't miss it. And here's one for your diary. On Thursday and Friday evening, the 16th and 17th, a slender young crescent moon slides up past Regulus and then Venus low in the western twilight. A beautiful photo opportunity.
For the early risers, the pre-dawn east is where the planets are congregating. Saturn is up after midnight and high before dawn with its rings tilted nicely for small telescopes, and Mars is gliding right past Aldebaran in Taurus this very morning, two reddish points of similar brightness, about 5 degrees apart. A lovely color comparison with just your eyes.
Dark skies, a brilliant evening star, and a red planet racing a red star. Not a bad week's programming from the universe.
And that's Astronomy Daily for Tuesday, the 14th of July. All our episodes, show notes, and the newsletter are at astronomydaily.io. And you'll find us across social media as @AstroDailyPod.
If today's episode sparked an opinion, and let's face it, space mirrors and UFO councils will do that, come tell us about it. We read everything. I'm Avery.
And I'm Anna. Thanks for spending part of your day with us. Until tomorrow,
Clear skies.